Okay, so finishing up question number 49, we found VA, the potential difference from charge A at the midpoint of the diagonals. We found the potential difference VB of charge B at the midpoint of the diagonals. We're now going to find VC, which will be the potential difference from charge C at the midpoint of the diagonals. Newton meters squared per coulomb squared, -8 to the -6 coulombs, and again over that 0.04243 meters. And when you do this, VC is also negative. It's negative 1.16912 volts. It's to the 6 this time. And now we're going to add them all together. 2, 3, 4, 5. 1, 2, 3. There might be a 0 or something here. 169. Oh, I lost a 9. That's what it is. 9. I knew that 2. Okay, so 1696912 volts. And so then to get the total, you're just going to add up the 3 of them, keeping the negatives. And when you add up the 3 of them, keeping the negatives, you should get negative 2.12, etc., times 10 to the 6 volts. I didn't write out all the digits this time. Okay? So potential difference is really easy. It's like fields and forces in the sense that you do to find the V's from each charge, but then you don't have to do the components for the voltage for the potential difference. You just add them together, keeping the negative signs. All right, next question was number 52 on that same page. And number 52 says, point A has an electric potential difference of 6 volts. So VA is 6 volts. When a charge of 2 coulombs is moved from point B to point A, 8 joules of work is done. So out here is point B, and I have a charge, and it's a pretty big charge, 2 coulombs. And I'm moving it from B to A. And to move it from B to A, I have to do 8 joules of work. Meaning it's not going to want to go to point A on its own. So point A must be a point of higher potential. And it wants to know, what's VB? Okay, so you need to call on your grade 11 physics a little bit here to remember that work done is equal to change in energy. In this case, the change in energy is going to be delta EQ. And so we know from an earlier video that V is equal to EQ over Q. So if this is delta EQ, then this will be delta V. So really it's telling us that the 8 joules is our change in the energy, and the charge that we're moving is 2 coulombs. So our delta V then is 4 volts. And we know delta V is equal to final minus initial, and it says you're moving it from B to A, so final will be A and initial will be B. And we're trying to solve for VB, so bring this over. So VB should be equal to VA minus delta V. So it should be equal to, I wrote down 60 there, but there's really a decimal. It will be equal to 6 volts minus 2 volts. So VB should be equal to 4 volts. Okay? Did I screw up? No, I did that in my head. This is 4 and this is 2. I should really look at the numbers. When I wrote this down, I knew it was going to be 2, and I had 2 in my head. So the delta was really 4 volts. There we go. Number 53 is kind of similar. 53 says a potential difference between point X and Y. Okay, so here's point X, here's point Y, and the potential difference between them, the delta V, is 12 volts. if a charge of 1 coulomb, so the little q that you're going to move is 1 coulomb, is released from point of higher potential and allowed to move freely to the point of lower potential, how many joules of kinetic energy will it have? So remember that it's this is delta V. So we know delta V should be equal to delta EQ over Q. So we can find delta EQ, the change in electric potential energy, should just be equal to Q delta V. Higher order math, 1 coulomb times 12 volts. So the change in electric potential energy will be 12 joules. And that change in electric potential energy has to go somewhere, and it goes to kinetic. So what it loses in electric potential energy as it moves, it gains in kinetic. Okay, and so what kinetic energy did it gain? 12 joules, because it lost 12 joules of electric potential energy, so it gained it in kinetic. And the last one is number 56, and we won't run out of time before we get this one done, I have a feeling. 56 is 2-point charges. One which is 6 microcoulombs, and the other one, which is -3 microcoulombs, are placed 8 centimeters apart. And it wants you to find the 2 points where the total potential difference will be 0. So if this is my number 1 and this is my number 2, this will be R1 for the point between them, and R2 will be 8 centimeters minus R1. So you're doing V1 plus V2 equals 0, or KQ1 over R1 equals KQ2 over R2. The K's will cancel, and it'll become Q plus the negative. Q1 over R1 equal to negative Q2 over 8 centimeters minus R1. Cross multiply. So it'll be Q1 brackets 8 centimeters minus R1 will equal negative Q2 R1. So Q1 times 8 centimeters minus Q1 R1 will equal negative Q2 R1. I bring this term over. So Q1 times 8 centimeters will be equal to Q1 R1 minus Q2 R1. Pull out the R1, Q1 minus Q2, and then divide both sides by the bracket. And so we will have R1 equals Q1 times 8 centimeters over Q1 minus Q2. So Q1 was our positive 6 microcoulombs times 8 centimeters over positive 6 microcoulombs minus a minus 3. On the top, that's going to be 48. On the bottom, it's going to be 9. 48 divided by 9 should be, for R1, 5.3 repeating centimeters towards 2. And then take that away from your 8 centimeters, and you should get 2.6 repeating, and that will be towards 1. Okay, so that's the point between them. But just like in the example 3 that we did, there's going to be another point on the line connecting them on the outside of the smaller one, and 3 is smaller than 6, so it's going to be out here. So we could call this distance R2, and so then R1 will become 8 centimeters plus R2. That'll be R1. And so you're going to do exactly what we did with the other. So it's going to be V1 plus V2 equals 0. So KQ1 over R1 will equal KQ2 over R2. Try not to lose that negative. The K's will cancel. So we'll have Q1 over